So for our next speaker, we welcome Benjamin Orsburn. Ben is a scientist with deep expertise in mass spectrometry, and his adventures most recently have included founding and being the chief scientific officer for Coral Reef Labs, as well as joining the junior faculty at the Johns Hopkins School of Medicine. But many of you may actually know Ben from his blog, which has been going on for more than 10 years now, Proteomics News at Blogspot. And I'm always inspired to read Ben's blog and get really excited about what technology he's spotted recently. And for that reason, I'm doubly excited to hear about what he's going to talk about today. So Ben, the show is yours.
Great, thank you. Let's see, share. Not so. Let's see, share. Aha, all right, thank you for that. Great, did that work? And can everyone hear me?
Yes.
Okay, great. So yeah, thanks for the invite. And yeah, I'm really excited to talk about setting up SCoPE on alternative platforms. And so, we've talked a lot about SCoPE over this, really great meeting. But, and SCoPE, really represents this kind of revolutionary cognitive leap, I think. But you'll learn very quickly to lead with the caveats, right? As you're meeting collaborators, when you start saying things like amplification and they start thinking about PCR, right? But we know what these caveats are, and now we're, 5 papers now where we've gotten to a really surprising level of consensus on what the limits are for how far you can amplify before you start having problems, which is great because mass spectrometrists can't seem to agree on anything. 25 years of debates on trips and ratios, right? But I really like this paper out of Forrest White's lab from Lawrence Staupfer, where not only because she really looked at an logical extension to one of the biggest problems that we have when looking at proteomic samples in terms of MHCs or phosphotyrosines, but where these nice illustrations that show, hey, if you boost too much, you're going to lose your ratio fidelity and that kind of thing. But the consensus across from the work from Nikolai's lab and everyone else is that for Orbitraps, after 200x carrier, you're going to run into all sorts of problems, right? And so I'm going to argue here that this is a peculiar characteristics of the specific physics of a peculiar mass analyzer. Now, and specifically, that it's a problem with the limits of intrascan linear dynamic range of the Orbitrap itself. So I'm going to say that as we continue to develop sample prep methods, I don't know that this is a hard limit that we need to that we should apply to other technologies that aren't based on the same kind of physics, right? And so, really just take a step back and think about how different the Orbitrap is from other mass analyzers, right? We're packing high-speed ions into a very small space to generate, essentially an extremely large flight path, right? So we're rotating ions around a central electrode, and then we're moving them back and forth, and we're applying so much voltage to them that they end up occupying these orbitals, right? And so ions of very similar mass per charge ratio are separating out over these tremendous distances, like near 1 million resolution here. You may be sending a kilometer, right? And something that's important here is that the split ion detector, as you see on the upper side of this little cartoon, is where the ions are recorded as they pass by. We do not make actual contact with the detector. We pass by it thousands and thousands of times. And the averages of that, as we translate the frequency across, this is what provides the great resolution and mass accuracy. But all along, we've known that there are some limitations to the Orbitrap in that we get decent sensitivity and we get acceptable speed, and those are really, there's an inverse relationship there. And as we've heard from everyone doing SCoPE-MS, we're using 300 milliseconds at 500 milliseconds fill time to offset the fact that the sensitivity really isn't all that great, right, for this instrument. And something that's been known all along, you go back to 2003, and all these papers were just trying to, hey, what is the Orbitrap going to finally be? And you find that, it was well known, it has an acceptable dynamic range, but it comes in a really small package that gets smaller and better all the time. And it dominates proteomics and mass spectrometry for good reason because of these characteristics, but it is very, very unique, right? And so I'm going to talk about some other mass analyzers on a very scientific scale based on their salient characteristics. And so Ion traps have good speed and on a resolution and the mass accuracy, but they have great sensitivity because as you're ejecting the ions, they actually strike the detector, right? In most cases, right? And you can offset those two things by ejecting things slower. Quadrupoles are very similar, and specifically to this quadrupole Orbitrap ion trap above. Where you get this resolution. You can't do anything about the mass accuracy really, but you get this great speed and great sensitivity because you've got just a focused ion beam aimed at your detector, and you just divert the stuff you don't want. And then, another not recent advance, but recently re-emerging in proteomics is the time of flight system, right? And you get good resolution, you get good mass accuracy, but historically we get this awful sensitivity, but great speed, right? And the sensitivity is just that, this flight paths, as you make them longer, the vacuum gets worse, and then they strike things and they don't get there. So, I kind of led with intrascan linear dynamic range. And the way I'm going to define that here is, within one spectra, what are the limits of linear response from high to low before things aren't linear anymore or so off that you can't compensate for them? And the way that I assess this is by setting up an extreme dilution range of isobarically tagged peptides. And here's one example. And I think there's people in the audience that have ran these very similar samples from me that I've shipped them so I could look at the different characteristics on different mass specs. But in general, there's 100-fold dilution between the 132 and 126. And this, as we mentioned actually a little bit earlier, I'm using the every other tag of the TMT Pro, and you get basically this linear response, right? And what I'm interested in is where does this go wrong, right? And another way to really assess the intrascan linear dynamic range is a great paper from Kaufman and Walker, and that link looks weird, but where they went through a bunch of small molecules that they cared about. And at the end, the punchline is that Orbitraps don't win. And in fact, they don't even really place well in terms of intrascan linear dynamic range. So I'm going to walk you through how, what I've done is in my 8 months as an academic in developing SCoPE-MS on a new platform. And we've all talked about the timsTOF, but in general, we're using trapped ion mobility to offset the sensitivity problem. So we're accumulating ions before TOF, and that kind of offsets everything. And the pros here is you get these great ion mobility separations. They're actually easy to forget about as using the device. You just got really fast, high resolution scans. And it can be fast while maintaining this great sensitivity. Now, cons that are very, very important here for SCoPE-MS is that you cannot scan high and low mass fragment ions simultaneously. It just doesn't work because of the physics of the front end and things. And the TOF is it's kind of mid-range. So you can get 42,000 resolution, and obviously I care about 42,000 resolution because that's what I need to separate the 127N and C from the TMT11 or 16 plex. I can get this if I spend several hours really just focusing on the tuning, but 100 LCMS runs later is not there. I've got coalescence and I can't trust that quant anymore. So and so that's it. And I think it's always worth noting here that data processing is a well-known challenge. It's improving, but it may at this point be a little understated how hard it is to work with this data. So if you're going to set up SCoPE, you should first figure out on a new instrument how to get really good TMT. And there's no better way to start, in my opinion, than the triple knockout standard from Harvard. You can get this from Pierce, and then you can run on your instrument and optimize things and change things. And then you just upload your data in their beautiful little shiny app at Harvard, and you can make these comparisons. And you're never going to beat the Orbitrap Fusion running MS3, right? Like, that's not what you're aiming for. What we were trying to do is, set up our instrument to be as good as an Orbitrap with a really good quad. And after a lot of work, we actually got the timsTOF there. It doesn't fit over here, and it's a theme. timsTOF doesn't fit a lot of places, right? So our ultimate SCoPE-MS platform, there's been great talks here on the LN1, but if you're on a budget, the same company has an R&D entry level system called the SciFlex Arrayer. It's essentially the liquid handling capabilities of the LN1. And you don't have the cameras, you don't have the sorters, but that's what we have. And so we sort across the street, 2,000 cells sorted out in a plate, sends them back $120. Bring them across in dry ice device, and we do all the prep there. So in general, actually, so let's look at how we set up the prep first. It looks like what everyone else is doing. I am missing a control here. We found that having a control between our carrier and our single cells is very important. And because I'm in a pharmacology department, everything we're doing is focused on understanding how drugs work, or drug toxicity, or how drugs are building, our cells are building resistance to drugs. So that's all that we're doing here. But behind the scenes, you get these, the timsTOF fixes its little problem with high and low mass by fragmenting each ion twice and then stitching it together behind the scenes. And that allows you to do some nice stuff like really narrowing your isolation range for the reporter ions and hitting them with a lot of collision energy. And you don't notice it until you're looking at, oh, Matthias Mann gets like 112 hertz and I don't. I get like 40 hertz for SCoPE-MS. And for normal TMT, we get much closer to 60 for this. But since we're using a little more fill time, well, on the timsTOF, it's ramp time. We use a little more ramp time. We get around 40 scans per second, which is really slow for a timsTOF, but is really, really fast for SCoPE-MS. And then we use the 9 tags for the TMT Pro. Chris mentioned this just a few minutes ago. We essentially just don't use the Cs. I use the Cs for generating spectral libraries. Right? And as Nikolai's mentioned, SCoPE-MS is just this balancing act between coverage and number of cells. And since I can only get 6 cells per LCMS run, and everybody gets a lot more, I make up the throughput with shorter LC gradients. And this is real data from one of our runs. And running 30-minute LC gradients. The chromatography system takes 15 minutes to load the samples. So it takes about 45 minutes for me to get data on 6 cells. So I'm getting 200 a day or 1,400 a week, but I still get decent throughput here with this setup. And so the data quality, it's right there with everybody else. I think, we're a cancer cell line. We can very typically achieve 1,200 proteins per cell. And, I hate using, cancer cell lines as a metric for anything, because they're so very strange. And I say reviewers have very universally disliked my use of spectral libraries for data dependent acquisition for everything that we've developed so far. But I do actually have to thank some reviewers because, we went back and used typical search engines, and actually the data is much better than that, and especially with MaxQuant recently enabling match between runs for TMT, that really the data is actually kind of transformative to our data. It looks really good. And again, I really like spectral libraries, and these are 2 peptides I care a lot about because I'm doing a lot of work with KRAS, and it's a kind of a terrible protein to work with all these little isoforms and all these things. But on the bottom here, you can see my mirror plots of my spectral libraries versus my real data, and you can see this little offset in the reporter region because I'm using one of the C tags that I don't actually use for my reporter ions. And I do offline fractionation, collect the data, and I use that to build my libraries across. And this is actually really new here. Connor Jenkins, when he was working for me in the past, it actually wrote some really smart Python scripts for looking at mass spectrometry data. And it just occurred to me on the phone with him last week that I could use that as a quick QC filter for my data. And I could set a signal and noise cutoff for my reporter ions and have it kick back, for each file, how many reporter ions or, ions in that range am I seeing through reporters? And, typically what I'm seeing across here is, there's something where, we always see something in the 126 in our blanks, 127 and 132, they look a little weird, but in general, we're getting lots and lots of spectra with reporter ions. And in terms of the benefits of more MS2 scans, if we compare some SCoPE data operating on a that's from a D20 Orbitrap using a slightly longer gradient, so we can match the number of peptide, the protein coverage. I'll direct your eyes to around 40% coverage where the D20 Orbitrap doesn't really pick up very many proteins that have that level of coverage, but the timsTOF does. So if you're hanging out with a bunch of nerdy doctors who are really concerned about their drug that binds to specific mutations of specific proteins, and you need high coverage to be able to say that you're actually knocking out this heterozygous, version of the protein, the higher copy number is really helpful. I don't know, it's helpful for all experiments, but it's really good for us. And so, we, in general, get this higher relative percent coverage. And I did kind of lead with the carrier limits. And so I think that this is maybe more typical now, but we start with a bulk cell lysate pool of each condition, repair it, quantify it, label it. And then this is a little bit different, but that and it's kind of frustrating. It feels like a waste of time. But what we do is we actually prepare a serial dilution of our carrier channel. We spike that into individual cells, and we run those replicates to work out where is the point where we get the most proteins and the highest coverage versus where's the point where we're actually affecting our single cell signal, right? So we really, for each experiment, especially with some of these proteins or cells that have like really disparate copy number distributions, we found that this is critical for us to get the best data possible, just really optimize this out. And I'll tell you what, like with having a whole series of choices to choose from, I have chosen for one study to use a 500X carrier, which I certainly would not have done that on the Q on our Q Exactive. So but just want to throw that out there. So in conclusion, I think that intrascan linear dynamic range is the biggest limiting factor holding SCoPE-MS back. And this factor varies between different instrument architectures, and it varies a lot. And if you take nothing else away from this talk, I want you to just think that SCoPE-MS can be successfully applied on hardware that is not Orbitraps. And in fact, it might actually work better on some of them. So that's it. Quick acknowledgements. Big shout out to Namanje for taking a chance on an obviously crazy person when she became department chair as her first hire. Uting is my first official grad student mentee. She's got some great stuff, a bunch of drugs for ASMS. Had a talk that was just accepted. Joseph Mertz 3 years ago got advice from Harrison Specht and generated plates and plates and plates of single cells for me and gave them to me and let me just destroy them trying to learn how to do SCoPE. And Arroyo, that robot actually belongs to him. He lets me use it all the time. Josh Cantlin has been really instrumental in helping us get throughput up, even though we're using his company's cheapest instrument. It doesn't actually belong to me, but he's been helping us all the time. And huge shout out to the Bruker team. And I've heard that there's a lot of people from Bruker in the audience. So if you're an important person at Bruker, I just want to say that you've got a really good team, but at the rate at which you're selling instruments, you need to hire them help before other people hire them, recruit them away because they're great, but you're going to work them to death. And last thing, if you've got a pharmacological application for single cell proteomics, please contact me. For better or for worse, if you go to that little search bar in the corner of most of your Windows computer and you type Ben Proteomics, it'll actually lead you to my contact information. I talk way too much. And I will leave you with these conclusions. Thank you for the invitation.
Can you hear us?
Yep, can you hear you now?
Yep.
Yeah, Ben, great talk. Thank you very much. I think you made my day just by that talk and your energy coming from the screen. I already kind of feel that you're nearby and already kind of stealing the best Bruker instruments right here in Massachusetts. I think you should definitely continue that. Definitely Orbitrap has some limitation that just physically cannot be, overcome. The question is about the coverage. You've showed the 25-minute gradient pre kind of complex chromatography. Why the number so low? Why you just not just pushing a little bit further? How many scans you have?
Oh, and that's a good question. And for me, I just and I think it's because I go to the single cell seq core, and that's where I sort my cells. And I feel like there's this pressure from those people who are doing thousands and thousands of cells that the whole time I've really generated this based on throughput, and a question, if I do 2 hours, if I spend 2 hours or 3 hours to get 6 cells, is that a good use of time? Especially an instrument that the grad students like to use during the week, and I just use it on the weekends because we have the flex, and so it does a lot of imaging during the week. So Uting is working with a giant ion optics column. She's using the Aurora 25 centimeter and low flow rates. And I think what she'll show at ASMS is we can push the coverage to higher levels there with that. But my focus really has just been throughput. How many cells can I get to?
Yeah, good. Thank you.
Any other questions?
Hey, Ben, it's John. I don't know if you can see me, but thank you for a wonderful talk. Just as an overview to your energy field talk, do you think that a Orbitrap and a Bruker timsTOF are going to be able to provide equivalent level performance, or do you think that in the end, one of those technologies is going to end up being more useful for very low sample amounts?
Ooh, I mean, that's a tough thing to speculate on. I think, honestly, I think, I commonly think, that we're always treating these instruments as if we all work in really good cores, right? That the instruments that are coming out that have the capacity to do large proteins and can do small molecules well and can do peptides well. I do wonder if this is a case where a fit for purpose instrument makes a whole lot more sense, right? That could we engineer something that was just good at that wasn't good at sequencing, that obtaining, a whole antibody, right? I think to really push the limits here, I think that what we'll end up seeing is, the successful architecture will have, a fit for purpose for this, that maybe is just angled toward doing this very well. I don't know if the solution is, who can build the most expensive mass spectrometer that can do anything. I think that it's going to be, if this technology really has a capacity to help patients, I think that, we're going to have to see an instrument that's, kind of like an ASIC, right? It's built for this, and, and then you bring the price down to a point where, we actually can use this to help patients in some way. Because you're not going to put the decked out timsTOF in any hospital, as a clinical instrument, or the Eclipse, right? It's going to have to be something fit for purpose. So if that's not the best way I can defer answering that question, I don't know what it is.
It was a great answer.
One more question.
Hi, Ben. David here. So you mentioned a little bit about the 40K resolving power, or 45K, and on good days you can push the instrument up to that. On lesser days, do you think you can tolerate some peak coalescence so long as you can discriminate with software the apex with a signal like the TOF signal, where modeling might be a little bit different than the Orbi signal for pulling out areas under the curves and so forth?
Maybe. And so I think that there's a really interesting analogous use of the phase constraint algorithm from that when Makarov was looking at what's the paper maybe 2 years ago, where he was looking at how low a resolution can we go with phase constraint and pull these apart, and realistic, and he really looked at like a 16 millisecond phase constraint, and he hit around 35,000 resolution or 40 or something like really close. And it does look like they work until you get to a 1-to-4 ratio. And then, the coalescence just kind of falls in. And I really thought like, okay, I could probably push this. And I've actually got a partially written manuscript, like, I was using the full 16 tags or whatever. But at this point, we can't use it. Use it on ours, and I realize that there's machining tolerances for different instruments that vary, and and maybe the Flex is different than the Pro. I do think it's very telling that the new single cell instrument from Bruker uses the TIMS unit from the Flex, and I think that is an interesting variable, because I've often wondered if how much different a Pro is, but I've never had hands-on with one. So I'm gonna lean toward probably not, unless you could get it stably to stay higher. That would be my.
Thank you. Cool.
Awesome. Thank you, Ben.